In this video, we're going to continue looking at the work done during the expansion and compression of a cylinder of gas. So to remind ourselves, if we have some gas and then the external environment has some external pressure and that pushes down on the gas, does work on the system, that is a compression where our change in volume is negative. And then the opposite of that, expansion, where we have the gas and the gas pushes up against the external environment, does some work on the surroundings, and increases its volume during expansion. So I'll add in there that note also, that for compression, delta V is less than 0. And for expansion, delta V is greater than 0. Okay, so what do we need in order for either of these processes to occur? Well, to compress a gas, we need it to be true that the external pressure is greater than the pressure of the gas. If not, then the gas would push outward on the surroundings and it would expand. But if the surroundings is pushing down harder than the system is pushing back, then you'll compress the gas until the pressures are equal, or you physically restrain it by some type of method. And then alternatively, to expand a gas, we have to have the gas pushing against the environment, and the system has to have a higher pressure than the surroundings to push it back and expand itself. So to expand, the external pressure has to be less than the pressure of the gas. Okay, so we notice that our formula for work has that work is equal to the minus integral of initial to final volume of the external pressure as a function of volume with respect to volume. So we have this external pressure there, it's P delta V. And in order to compress, it has to be greater. In order to expand, it has to be less. So you'll notice that for a compression, this external pressure can be anything as long as it's higher than the pressure of the gas. And so it can do a larger amount of work than is necessary to compress the gas. And then in the opposite case, the external pressure here has a minimum of 0. So if the gas was expanding against an external pressure of 0, then it wouldn't be doing any work because the external pressure is 0. So 0 times something integrated is still going to be 0. So there's a minimum amount of expansion work which is possible there, which is just 0. So what we're interested in is what is the minimum amount of work you can do and compress a gas, and what is the maximum amount of work that can be done during the expansion of the gas, and when do these two become equal. So to formally write that down, we have the minimum compression work and the maximum expansion work. Both of these will happen whenever the external pressure is approximately equal to the gas pressure for all values of volume. So as we compress this gas, typically it's going to get a higher and higher pressure inside of it, and it's going to become more and more difficult to compress. And so we need to have a larger and larger external pressure in order to keep compressing the gas further. But if we do it in such a way that the external pressure is equal to the pressure of the gas at all points, then we're doing the minimum amount of work that we could possibly do. And similarly, during expansion, this internal pressure has to be larger, so the minimum amount of expansion work is also when the external pressure is approximately equal to the internal pressure during this entire process. And when those are true, we have that the minimum expansion work is also going to be equal to the maximum the minimum compression work is also going to be equal to the maximal expansion work. So the minimum compression work is going to be equal to the maximum expansion work. And when we have a situation like this, we could take our gas, expand it out here, do the maximum work possible, then take the gas and compress it, doing the minimum amount of work possible, and those two would be equal. And if we did it in that way, such that we did the maximum expansion work, then the minimum compression work, we would have done no net work, because those two are equal to each other. Well, at least in magnitude. I should put magnitude bars there because they would be opposite signs. Okay, so if we have a situation like this, then this would be referred to as a reversible process. Because essentially we can do this back and forth as many times as we want, and if we end up at the same volume that we started with, then we've done no net work overall. So a reversible process would be one which satisfies conditions like that. But more formally, it'd be any situation where we have only infinitesimal changes, infinitesimal system changes over functionally an infinitely long time. So you can't actually achieve completely reversible expansion and compression. You can only approach them in a limit. Because in order to actually achieve this, you would have to go extremely, extremely slowly and make sure that the pressure, the external pressure and the gas pressure were extremely, extremely close at all points along the expansion or along the compression. So it's kind of an abstraction, but it's a nice limit to think about. Just like absolute zero for temperature is a nice limit. We can get very, very close to absolute zero, but we can't get exactly there. Okay, so if we have a reversible expansion or compression, we have reversible expansion or compression work, then we're going to say that P external equals P gas for all points along volume. We know that for an ideal gas, as we're assuming the cylinder to be, PV is going to equal nRT. And so this integral here of P external, well, our P external is just going to equal our P gas, and our P gas, based off of this equation, is just going to be nRT over V. So the integral that we need to do is going to be minus integral from initial volume to final volume of nRT over V with respect to V. Okay, so our final result then is going to be this nRT is just going to pull out on the end as is this minus sign. Then we have the integral of dV over V, which is going to be the natural log of V. And then from the initial to final conditions, it's going to give us final over initial. If you work out this integral, you should get this result. So what we have just done is found for the reversible expansion or compression of a gas, the work is going to be minus number of moles of gas times R times temperature times natural log of the final volume over the initial volume.